Welcome to Brain Vision.
The objective is to prove various properties of the Wigner Seitz cell for different types of Bravais lattices, including the shape of the cell, the ratio of diagonal lengths for parallelogram faces, the edge length of the polyhedron bounding the cell, and the regularity of hexagonal faces in the body-centered cubic lattice. In a 2-dimensional Bravais lattice, the Wigner Seitz cell is the region of space that is closer to a given lattice point than to any other lattice point. To construct the Wigner Seitz cell, we draw lines connecting each lattice point to its nearest neighbors and then draw the perpendicular bisectors of these lines. The intersection of these bisectors forms the Wigner Seitz cell. In a 2-dimensional Bravais lattice, there are only 5 possible shapes for the unit cell: square, rectangular, rhombic, hexagonal, and oblique. However, the Wigner Seitz cell must be symmetric with respect to the lattice point it encloses. This means that the only possible shapes for the Wigner Seitz cell are those that have rotational symmetry about the lattice point, which are the hexagon and rectangle. In a face-centered cubic FCC lattice, the Wigner Seitz cell is a rhombic dodecahedron. Each face of the rhombic dodecahedron is a parallelogram. To find the ratio of the lengths of the diagonals of the parallelogram, we can use the Pythagorean theorem. Let it be the length of the side of the conventional cubic cell. The length of the diagonal of the parallelogram is equal to the distance between the centers of two opposite faces of the conventional cubic cell, which is a square root 2. The length of the other diagonal is equal to the distance between two opposite vertices of the conventional cubic cell, which is a square root 3. Therefore, the ratio of the lengths of the diagonals of the parallelogram is square root 2, 1. In a body-centered cubic BCC lattice, the Wigner Seitz cell is a truncated octahedron. Each edge of the truncated octahedron is equal to the distance between the center of the conventional cubic cell and the center of one of its faces. Using the Pythagorean theorem, we can find that this distance is a square root 1/2/2, whereas the length of the side of the conventional cubic cell. To prove that the hexagonal faces of the BCC Wigner Seitz cell are irregular hexagons, we need to show that all the sides and angles are equal. Each hexagonal face is formed by truncating a square face of the octahedron. The side length of the square face is a square root 1/2/2 as found in part D. The side length of the hexagon is equal to the side length of the square face, which is a square root 1/2/2. The angle between two adjacent sides of the hexagon can be found by considering the dihedral angle between two adjacent square faces of the octahedron. This angle is equal to the angle between the body diagonal of the conventional cubic cell and the face diagonal, which is 109.47 degrees. Since the hexagonal face is formed by truncating the square face, the angle between two adjacent sides of the hexagon is equal to 180 degrees minus 109.47 degrees equal to 70.53 degrees. Since all the angles are equal, the hexagonal faces of the BCC Wigner Seitz cell are regular hexagons.